Alright, page 34, crystallographic direction and planes. Coordinate system is developed to determine the position in space. In crystallography, the unit vectors are chosen to be coincide to the unit cell edges from one corner. Coordinate system is developed to determine the position in space. In crystallography, the unit vectors are chosen to be coincide to the unit cell edges from one corner. Chosen to be coincide to the unit cell edges from one corner. The length of the unit vectors and angular dependence between unit vectors are coincide to the crystal system. The length of the unit vectors and the angular dependence between unit vectors are coincide to the crystal system. Okay, so I get that coordinate system is developed to determine position in space. That's what I get. And I get that unit vectors are chosen to be coincide to the unit cell edge from one corner. Okay, so from the origin, it is going in XY direction. The length of unit vectors and angular dependence between unit vectors. Length of unit vector and angular dependence between unit vectors are coincide to the crystal system. Yes, basically you determine the coordinate of the crystal system, and then you set up what are the unit vectors. Position of a point. What I say is, after the coordinate system based on unit cell of the crystal being constructed, the position of a point in space can be defined by the length of projection on the coordinate axis. For three-axis system, the coordinate QRS according to each axis are used to define point position. After the coordinate system based on unit cell of crystal being constructed. Coordinate system based on unit cell of crystal being constructed. The position of a point in space can be defined by the length of projection on the coordinate axis. Oh yes, that's how you define the lattice vector. For three-axis system, the coordinate QRS according to each axis are used to define point position. So Q is along X direction, and R is along Y direction, and S is along Z direction. That's why we call it QRS. And on page 36, crystallographic direction. On my left hand side is a crystal structures. It's looking like a triclinic crystal structures, triclinic lattice. So a crystallographic direction is the vector between 2 points. Crystallographic direction is the vector between 2 points. All parallel directions are equal. We use the vector passed through the origin to represent all parallel direction. Vector passed through the origin to represent all parallel direction. The parameter UVW are used to describe the crystallographic direction. The 3 numbers are projection on of the vector along the 3-unit vector. The 3 numbers are smallest integers without common factors. Okay, so not sure why we last slide was QRS, coordinate QRS, 3-axis system coordinate QRS used to define point position. So QRS is used to define point position, but UVW are used to describe crystallographic direction. So QRS are used to define point position, but UVW used to describe crystallographic direction. And crystallographic direction is the vector between 2 points. The 3 numbers are the projection of vector along the unit vectors. The 3 numbers are smallest integer without common factors. So OA, OB pass through origin. OA, OB direction AB should be moved to OC. Direction AB should be moved to OC. Direction AB should be moved to OC. The 2 directions are same. Yeah, so that's gonna be 1, -1. Okay. So OA is 1, 2, 3. So 1, 2, 3. So OA is gonna be 1, 2, 3. Okay. And OB gonna be 2, 3, 2. OB gonna be 0, 3, 2. 2, 3, 2. 2, 3, 2. Okay. And direction AB should be moved to OC. Okay. So QRS are used to describe position of a point in crystallographic direction in coordinate QRS. QRS are used to define position of a point, and UVW are used to define the direction from a point to a point. Describe crystallographic direction. And page 37 for 7 is about crystallographic direction in hexagonal crystal. Crystallographic direction in hexagonal crystal. hexagonal crystal contain 3 basal plane, right? And then hexagonal plane, primitive, hexagonal primitive, and then with a C height. So because of the threefold symmetry in the basal plane, in hexagonal crystal, 4 unit vectors are normally used. Because of threefold symmetry in basal plane, in hexagonal crystal, 4 unit vectors are normally used. So there are 4 unit vectors in hexagonal crystal. 4 unit vector using in hexagonal crystal: A1, A2, A3, and A4, or A1, A2, A3, and C. And we also use UVW. Projection is taken to be parallel to other coordinate axis. Projection is taken to be parallel to other coordinate axis. Projection is taken to be perpendicular to coordinate axis. Projection is taken to be parallel to other coordinate, meaning the projection of A1 on A2 and projection of A2 on A1, and the intersection right there is forming a vector, a direction vector from O to that intersection point. Projection and the projection for the definition on the right hand side, projection is taken to be perpendicular to coordinate axis. Taken to be perpendicular to coordinate axis, meaning that coordinate axis. So let's draw an axis that perpendicular to A2, perpendicular to A1, and perpendicular to A3, and the perpendicular and the intersection of 3 perpendicular lines to the origin, forming us a direction vector. UVTW. UVT. Not sure what is the W. W may be the 4 unit vector. So UVT stand for A1, A2, A3, and C. On page 38, example of 3-axis and 4-axis indices for, of course, hexagonal crystal. 3-axis and 4-axis indice. For 3-axis indice in hexagonal crystal, U from, V from, W from, right? A1, A2, A3, and C. So the direction is forming by the projection of the vector on the other axis. Intersection with A1, A2 are 1, 1, 0, right? 1 on here and 1 on here, so 1, 1, 0. You gonna be so this mean that how if this is a 1, 1, we have a 1, 1, 0 intersection, how are we transforming a UVTW 4 indice to 3 indice, 3-axis to 4-axis indice? Okay, so how are we doing that. So if we have a vector, right, a vector in hexagonal crystal, how are we going to get the vector in 3-axis into 4-axis index? We need all vector have 3-axis index, but in hexagonal axis index we need to translate the 3-axis index into 4-axis index for hexagonal crystal. So let's say for the formula we have u equal to 1/3 2 prime minus v prime, v equal to 1/3 multiply with the product of 2v prime minus uv prime, and t equal to negative 1/3 times the product of u prime plus v prime, and w equal to w prime. And in the other hand, there is a formula for u from by calculate by from u minus t, and v prime equal to v minus t, and w prime equal to w. So we have, let's say a1, a2, a3. We have, and t is equal to u negative u plus v. How maybe this is a substitution, but this is also needs to be here. T equal to t, you can calculate from negative 1/3 u prime plus v prime, or equal to just negative u negative u minus v. Intersection with a1, a2, a3 axis are 1/2, 1/2, negative 1. So a2, a3 axis are 1/2, 1/2, half, half, and negative 1. Negative 1 with this right here. And 0. Alright, coming back, keep going. Crystallographic plan, page 39. All parallel planes are equal. All parallel planes are equal. A 3-number index XCL is used except for hexagonal system where 4-number index is used. Okay, all 3-number index used except for hexagonal system where 4-number index used. Equivalent plane inside unit cell is not passing through the origin should be constructed to determine XKL. Equivalent plane inside unit cell and not passing origin should be constructed to determine XKL. First of all parallel planes are equal. Okay, a 3-number index XKL is used except for hexagonal system where 4-number index used. So that means all systems should have 3 index except for hexagonal system. Equivalent plane inside unit cell. Equivalent plane inside unit cell and not passing origin should be constructed to determine XKL. Of course, all equivalent plane inside cell but not passing origin should be constructed. XKL, the plan, notice that plan is in parentheses, are determined by recording the intersect of the plan and 3-axis. Intersect of the plan and 3-axis. Take the reciprocal and intersect numbers and convert them to integer without common factors. XKL, plan XKL are determined by recording the intersect. So number 1 intersect, then take reciprocal and convert to integers. So the step is intersect, right? Let me type it out. so it's easier for us to use. Plan how to find one is intersect, two is reciprocal, and then convert into without factors. Intersection of red plans with three axes are 1, 1, 1, 1/2. Reciprocals are 1, 1, 2, so plan indi is 1, 1, 2. Clear. All right, page 40, important plans and spacing between plans. Important plans and spacing between plans. Cubic system with the edge or side is A. And the plan on the side plan on the y-axis is 0, 1, 0, wherever that is. Pointing out is positive. 1, 1, 0 is when it's a 1, this is 1, plotting here. So 1, 1, 0. This is the 1, 1, 0. Yeah, but it's shifted. It's still 1, 1, 0. And 1, 1, 1 is 1, 1, 1. Right here, 1, 1, 1. Pointing right that. And similarly, this one, 1, 1, 1. So 1, 1, 1. Similar important plan and distance spacing between plans. So far we discussed the important plan already. That is 0, 1, 0, which is on the y-axis pointing out, and 1, 1, which is the intersection between x and y-axis, forming a diagonal pointing xy direction. And 1, 1, 1, 3 intersection, whether it's forming by the doesn't matter the location and how weird it looks. If it's similar, it's the same. Interplanar distance between XKL plan are written as DXKL. Interplanar distance between XKL plan are written as D with little XKL. So the interplanar distance of the two plan 0, 1, 0 is A, right? And the interplanar distance between the two plan 1, 1, 0 is square root of 2 over 2A. And interdistance between the two plan 1, 1, 1 are negative 3 over 3A. So A square root of 2 over 2A and negative 3 square root of 3 over 3A. In cubic system, the interplanar distance is interplanar distance of plan XKL, two plan XKL, interplanar distance between two plan XKL are the A distance over the distance x direct over the square root of distance in x, in y, and in z. The quadratic form, the magnitude of quadratic magnitude of vectors, basically what I mean. Magnitude of the vectors, it's very similar. It's a vectors. Imagine this is a vector and this is just a magnitude. So the distance A over the magnitude of the vectors between two plan of the plan direction. the plant, the interplanar distance of the plant, the vector distance between of the plant. Tetrahedral and octahedral interstitial. Tetrahedral and octahedral interstitial. Tetrahedral. Tetrahedral. So the first group is nothing. Second group is the draw, and the last group is the egg. So this is the second group, where is A equal B equal C, A equal B but not equal to C, and tetrahedral is where A equal B equal A alpha equal beta equal 90 degree with a gamma equal 90 degree, and octahedral. Well, that's hexagonal. This is octahedral. Coordination number 4. 1, 2, 3, 4. Coordination number 6. 1, 2, 3, 4. Wait. Coordination number 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So not counting. The interstitial here is not being part of the coordination number. Coordination number simply is the number of the atoms, the bigger atoms. There's only one interstitial in each of the structures on page 41. Coordination number 4 means 4 atoms. Coordination number 6 means 6 atoms. And in the tetrahedral interstitials in FCC, tetrahedral interstitial in FCC. So FCC, face center cubic. This is the crystal structures of the FCC, and this is the lattice of the FCC, and this is the lattice and basis of FCC, and this is the I don't know what is the last one. There are 8 tetrahedral positions in an FCC unit cell. Tetrahedral position. Again, tetrahedral is A equal to B, equal to not equal to C. I can always going back and prove it to you. Triclinic, tetragonal, not tetrahedral. Tetrahedral, tetragonal. There are 8 tetrahedral positions in FCC unit cell. What does tetrahedral mean? What does tetrahedral mean? Tetrahedral. Triangular face or pyramid. Tetrahedral refers to a shape or geometry that has 4 triangular faces, like pyramid with a triangular base, tetrahedron, tetrahedral interstitial. Well, tetrahedral interstitial site is an interstitial site that is surrounded by 4 host atoms at the corner of tetrahedron. So tetrahedron is a 4. A tetrahedral interstitial is an interstitial between 4 atoms with 3 atom basal atom and 1 atom on the top. And octahedral is interstitial is the interstitial between 6 atoms. This interstitial is being sandwiches between the two basal band. So tetrahedral interstitial, the interstitial between 4 atoms, 3 in the bottom and 1 on the top. Right here. Okay, right here. This one being sandwiches. Okay, so just remember that there are 8 tetrahedral positions in FCC unit cells. In FCC unit cell, there are 8 interstitial, 8 tetrahedral interstitial. Oh no, there are 8 in tetrahedral position in FCC unit cell. So that doesn't mean there are 8 tetrahedral interstitial. There are 8 interstitial in FCC. There are 8 tetrahedral position in FCC unit cell. One, two, three, four, five, 6, 7, 8. Wait, so that also means there are 8 tetrahedral interstitial in FCC unit cell. Because there are 3, this is 3 right here. Here. Yeah. 1, 2, 3, 4. 1, 2, 3, 4. And octahedral interstitial in FCC. 6 interstitial in FCC. There are 4 octahedral position in FCC unit cell. 4 octahedral position in FCC unit cell. That is FCC, and this is FCC with body centers, and this is an FCC, but with also a body centers. There are 4 octahedral positions in FCC unit cell. I'm not sure about 4. I see a lot. I don't see 4. I see a lot. 4 octahedral. Coming back later, not sure about this one. Last 2 slides, couldn't imagine what they are. Alright, for base 44. Tetrahedral interstitial in XCB. Tetrahedral interstitial in XCB. So every 4, you will have 1. So this is 1, 2, 3, and this is 1. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 1, 2, 3, 4. 1. So right here, 1, 2, 3, 4, and then you have 1. Tetrahedral interstitial. Oh man, I'm not sure how you draw this. go 1. Here we go 2. And then how you gonna find another one? Yeah. Now, I'm not sure, man. There are 2 right here. Okay. Well, let's review this one again later. Octahedral intertissue in XCB. There are octahedral. How many? Here is 2. Octahedral. I review later. Okay, so summary: page 45, page 44, page 43, page 42. So 1, 2, 3, 4. Last 4 page, I don't get anything. I don't really understand about the last 4 page. Yeah, not sure about last 4 page. It's about intertissues. Tetrahedral intertissue and octahedral intertissue. Tetrahedral is intertissue is the intertissue between 4 atoms, 3 on the bottom and 1 on the top, and octahedral intertissue is the intertissue between 6 atoms, 3 on the bottom and 3 on the top.